In this video, we're going to be doing an AP Physics 1 FRQ for Unit 3 Energy. We have a block of mass M that starts from rest at point A height h above the ground. The block slides down a frictionless curved track and then enters a rough horizontal section of length L. The coefficient of friction between the block and the rough section is mu k. After leaving the rough section, the block moves onto a frictionless horizontal surface and then compresses a spring constant, k. The spring is initially uncompressed. We want to derive an expression for the speed of the block when it is at the bottom of the frictionless curved track, just before it enters the horizontal rough zone. So when the block is over here. We can start off with the fact that our block is going to start from rest. So VA is equal to 0. Our initial height is going to be YA, and that is equal to our height. So we also have that at the bottom. We're going to set our height equal to 0. So YB is equal to 0. Additionally, we know that because the track in this section is going to be frictionless, we're going to have mu k is 0. So in this section, the mechanical energy is conserved. So we are going to set our kinetic energy initial plus our potential equal to our final. After this, we know that initially, when we are at our maximum potential energy, we have no kinetic. And for this, we are going to have 0 potential because we're going to be at a height of 0. After this, we have just mgh, and we have 1/2 mass velocity b squared. Now, after this, we can cancel out our m's on both sides. We get gh is equal to vb, or 1/2 vb squared. You can multiply both sides by 2. And we get that 2gh is equal to vb squared. If we take the square root of both sides, we get that vb is equal to the root of 2gh. So what we see is our gravitational potential energy. It turned into kinetic energy on the frictionless track. Derive an expression for the work done by friction on the block when it moves across the rough section. So when we are on the rough section, we are still going to have the block being perpendicular to the surface. So you're going to have a normal force perpendicular to the point of contact. And at the center of mass, you're going to have the force of gravity acting downward, which is equal to mg, aka the weight of your block. So we know that kinetic friction can be represented as mu kinetic friction times the normal force. In this case, our normal force, we are only going to have the force of gravity acting in the vertical direction. So if we take the summation of our forces in the vertical direction, we have no acceleration. Acceleration y is equal to 0. So mass times 0, acceleration is equal to 0. Therefore, we know Fy, we had upward is Fn, and then downward we have mg. So that means that if you add mg to both sides, you can see that that is how we get our normal force is equal to mg. So here we have mu k, and then we're going to substitute an mg right there for Fn. After this, we know that for our definition of friction, friction always has a direction opposite to your motion. So if you're going to the left, you're going to have friction in the right. So that means if we draw a vector between the two, for example, we are going this way, we're going to have friction pointing this way, and we're going to have our force pointing this way. If we find the angle between these two, that is 180 degrees. So our formula for the work done by friction is going to equal to the force of friction times the displacement that we traveled times cosine of the angle between these two vectors when you add them tail to tail. And that's important because you don't want to take the vectors where you're doing this, because that's not going to be correct. You have to find the vectors when you put them at the very end to end. So that's going to be cosine of 180 degrees. Cosine of 180 degrees is going to be here. You're going to be at -1. So you are going to have negative force of friction times displacement was L, and we have -1 here. So this is what we get. If we substitute this in, we have work done by friction is negative. Our force of friction here is this. So we're going to take that. We have mu k mg times L. So this is our work done by friction. So this makes sense because we have our friction is going to remove mechanical energy from our block track system. Now, derive an expression for the speed of the block immediately after it leaves the rough section. So after it leaves the rough section, we are going to have energy with non-conservative work. What that means is that you are not going to be maintaining the same amount of energy that you had before that you entered into this area. So then energy initial plus our work is going to be non-conservative, is going to equal to our final. So we know that when we are at the beginning of the rough section, we are going to have the kinetic energy initially is equal to 1/2 the mass times the velocity b squared, and then we're going to have u initial equal to 0. Then when we are at the end of the rough section, you are going to have kinetic energy final is equal to 1/2 mass vc squared, uf is equal to 0. So then we can set these equal to each other. So we're going to have 1/2 mv b squared plus wf is equal to 1/2 mvc squared. We know that we have vb squared here, and we also found this earlier. So vb squared earlier was equal to 2gh, where we got the speed. So we also know that work done by friction is negative mu k mgl. So then if we substitute these in, work done by friction here, we get this expression, 1/2 m times 2 times gh minus mu k mg times l is equal to 1/2 mass vc squared. So you can factor out m and g here, So we get mg out here times height minus mu k l is equal to 1/2 mvc squared. After this, you can just cancel out your m's from both sides, and we have gh minus mu k times l is equal to 1/2 vc squared. After this, we can multiply both sides by 2 in order to get rid of that 2 over there. So you're going to have 2g times h minus mu k times l is equal to vc squared. And then after this, we're going to have vc is equal to the root of 2g times h minus mu k times l. And this is only going to be valid if our height is greater than mu k times l, because otherwise you would have height minus something that would make h negative. And then if you make h negative, you would be taking the square root of a negative. So that would not work. And this makes sense because the block's energy after friction equals its original gravitational energy, Ug, minus the total energy lost to friction. So for our next question, we want to derive an expression for the maximum compression x max of the spring once our block here is going to go over here and hit the wall, or cause the spring to compress as much as it can. So what we know is when you are at the state of max compression, your V is going to equal to 0. So that's because you are all the way at an amplitude, and at that moment, you're momentarily going to stop, and you're going to change direction from going in one direction to the next. And again, your velocity, it has to pass through 0 in order from going from a positive direction to a negative direction, which is how we know that the velocity is equal to 0. So we know that before our spring compression, we have K initial is equal to 1/2 mvc squared. And then when you are at max compression, you are going to have here that your Kf is equal to 0 and your potential spring is 1/2 K times your displacement maximum squared. So we have conservation of energy because we have a frictionless section. So we have these equal to each other. 1/2 k times x max squared. So then you can just substitute in. We know that VC squared is 2g times h minus mu k times L. So you're going to take this and substitute it in right there. You have 1/2 m times 2g h minus mu k times L. And that's equal to 1/2 kx max squared. So on the left side, we can simplify this. We have mg h minus mu k L, and this is equal to 1/2 kx squared max. After this, we have a 2 over here. So we can multiply both sides by 2 and cancel that out. So we have 2mg h minus mu k L is equal to kx squared max. After this, you divide both sides by k, and we have kx squared max is equal to 2mg h minus mu, or never, that's not there. So you have kmg h minus mu k L all divided by k, and then x max, just your square root. So square root of that. All over k. So this makes sense because our US, spring potential energy, it comes from the mechanical energy left after the friction moves the energy. So determine the minimum height min needed so that the block just reaches the spring but does not compress it. So if it just reaches the spring, that means that the spring is going to be at VC is equal to 0. So that means that the block has no kinetic energy after it leaves the rough section. So you're going to have VC squared is equal to 2g times h minus mu k L. So if we set VC equal to 0, that's equal to 0, and you get 0 is equal to that whole thing. And you can divide both sides by 2g. You see that you're dividing something by 2g, that just cancels. Now we can just add that mu kl, and you have your h is equal to mu k times L. So that means your height minimum is equal to mu kl. This makes sense because our UG initial is equal to exactly the energy lost to friction. So that makes sense. That's your H min. Now, our next question is, suppose the rough section length L is doubled while all these variables remain the same. Describe how the maximum compression of the spring changes and justify your answer. So we know that our original spring compression is equal to x max all divided by k. So our new length is L prime, and our new compression is x prime max. All divided by k. So then all you do is substitute in. So that is your answer. That's x prime max. So what we can see is the difference between the two is this section here, the only difference we see is that h minus 2 mu k L, that's less than h minus mu k times L. So that means that x max is going to be less than x max. Therefore, maximum compression is going to decrease. So that means that if you have an h equal to 2 mu k times L, then you have an x prime max that is equal to 0. So that means the block reaches the spring. Now, if h is less than 2 mu k L, that means that the block does not reach the spring. This makes sense because if you double L, that is going to double the energy removed by this friction. Now, suppose instead the mass of the block is doubled while all other quantities remain the same. Determine whether the maximum compression of the spring increases, decreases, or stays the same. Justify your answer. So again, we had our original compression is equal to x max, which is equal to the square root of 2 times mass g, h minus mu k times L, all divided by k. We know that our new mass is going to be m prime, aka 2m double. So that means if our new compression is going to be x max prime, which is going to be 2 times 2 mass, you just replace m, g, and you keep everything else the same. So yeah, you just have that 2. And since we know that we had that original, the only difference was that we have a multiplication by the root of square root of 2. So x prime max is equal to the square root of 2 times x max original. So that means that this spring compression increases by factor of this. So what we see is that if you 2x your mass, that means that it's going to 2x your UG, and also it's going to 2x your energy lost from force of friction. But your energy is still going to be proportional to your mass. So your spring stores more of the energy and it compresses farther.